is just green light. Any ideas?
Cheating.
Cheating. Anybody else?
Look,
Look, okay, at least 2, 3. Let me tell you a little bit more about this. She told me I'm not bad. But I asked her to do these things. She didn't come with me. Pretty ordinary looking person. Modestly dressed, I'd say she was between 35 and 40, moderate height. She had a green dress, but not really nice shape. Does that help you?
how many people did you ask?
Well, let me tell you a little bit more.
Okay, actually, maybe the words Las Vegas.
Same afternoon, there was a gentleman who also did the same thing. But got hit sometimes.
Magician's trade show.
Coin only had coin only had hips.
There's more in the story. These two people were from an audience of about, I guess, 200 people who all been asked to do this experiment. So the question was quite appropriate underneath the ask. And some people got none, some people got 4, and these two people were able to do 7 in a row. They retired. And you'll ask, what does that have to do with psychology? If I can explain that to you, then that's really all that I hope to do today. But I'll try to give you some details, and then you can have a chance as well. Here's a record you've probably seen before. It's an account of earthquakes that have occurred on the San Diego near Parkfield, California. And this is the basis of what's known as the Parkfield earthquake prediction. These are earthquakes about magnitude 6. They should occur within about a 40 or 50 kilometer area. And the base fall on a pretty linear progression, the average time between 2 years. And this slide came from a diagram on the web from USGS, but it was made in 2001, which is what there's an arrow there. And simply by taking that line forward, one can get a mean recurrence time and some uncertainties on that recurrence time and still get forward. And that was done kind of in retrospect. This story, these data were put together after 1984, which is the time you would get if you projected that forward. But the USGS came up with a prediction saying that there was a 95% chance of another earthquake like this by 1992. And it didn't happen, but there was an earthquake in that place, magnitude 6, in 2004. Some people say that was a late success, and some people say with still or any prediction. Some notes on the data. Those are the data that we already saw. Those are the intervals. You see they're not really so big. And this prediction was made by ignoring the 12 years and 32 years. Ignoring the 12 years of the earthquake came early. It wasn't an excuse for what might have occurred. Magnitude about 6, and that's an important consideration here because earthquakes of magnitude 6 take place about 10 times as frequently as magnitude 7, and about a tenth as frequently as magnitude 5s. So a little bit of uncertainty in magnitude can make a fairly big difference in the first 3 events were not recorded seismically. We didn't have seismographs in 1887 and 1881. 1881 earthquake was reported by a traveling minister on horseback who was cracking the ground, and the magnitude estimate of that one was made by analysis of these other earthquakes. The same minister mentioned that there was there's a strong smell of sulfur. Which make people believe they were unused, more unused mind. Science at that time. And the idea that this sequence of earthquakes was periodic came from a rancher who was having coffee at the Park Food Cafe with one of my colleagues out in the end. This rancher said, there's something about earthquakes here. We seem to come about every 20 years. And so Alan Lynn went and looked in the newspapers and found evidence about these stories and came up with those dates that you saw. Well, here's a map of earthquakes that have occurred. Extrapolate backwards and you would count it. There would be about 200 magnitude 5.5 or greater earthquakes since 1850. And of that 200 and some earthquakes, I would bet any of you could find something remarkable about a sequence of earthquakes when they occurred or whatever. And in fact, in a place near Long Valley, under USGS scientists found the sequence of 1905 earthquakes. 5 of them that occurred about 18 months apart, apparently quite periodic. Published a paper on this, suggested that maybe another one was coming in the next 18 months. And it's been now 25 years since that sixth one has been. So anyway, keep a look at this and find lots that would be interesting and seem to show patterns. And so we get back to this question, how many people did he ask? If you fish through these data, you'll find something like that. My hypothesis is that these data, partly, that seem to show this regular pattern were cherry-picked. Through the data, an interesting story came up. Even if the earthquakes are absolutely true, and even at this point, flip a coin and got hits 7 times a month, there's no big deal. That's what you expect. And the 2004 earthquake, I would argue, isn't any big deal. It doesn't validate the prediction in any sense of the. First of all, it's 6.4 sigma too late. Therefore, there was no real definition of what it was that was happening. The prediction was something like the ones that had happened before. And that's just an example. That isn't any kind of set in which you can do any kind of statistics. The idea of fitting a line through this is kind of, off base right at the very beginning. Initially, it was based only on these previous events, but the 2004 event was different. A big thing was making a prediction about the apparent similarity of these previous earthquakes, even though some of them were not observed directly except by this industry. And nevertheless, they were assumed to be pretty much identical. And the last two of this sequence, the T.2 and T.4, were very, very similar in some part of the form. So, and the fact that it was a magnitude 6 has given a lot of press because that's what the prediction was. But when you think about it, that's no big deal either, on account of the fact that they weren't counting anything much smaller than magnitude 6. And when you take a set of earthquakes that is about magnitude 6 or greater, most of them are going to be about magnitude 6 because of the fact that the big ones are more rare. In fact, if you look at the statistics of the earthquakes that occurred in that area, I show 2 different versions of this, one before the 2004 earthquake and one after. And they fit what we know as the Gutenberg-Richter behavior. Magnitude on the horizontal axis and the log of the number of earthquakes on the vertical axis, and gives a nice straight line. And you can throw a dart at the globe. You spin the globe, throw it around, hit a place, expand the circle until it includes 100 earthquakes, and plot them in this form, and they're going to look like that. It's just not fully explained fact and nature of what happens. And sure enough, before 2004, the earthquakes looked like that. And after 2004, they still look like that. You notice you had good eyes. The green line after 2004 shows the range, the 95% confidence range for that kind of count. And so when you could have a magnitude 6.5 with weight there, so we can take some observations, make a forecast based on that, and all that forecast is really a projection of what happened in the past. So we really never and if that were all there was to it, then I wouldn't know too much, but I'm going to show you some data from this group of people who are eminent geophysicists and statisticians. Mark Matthews is somebody who's got impeccable credentials in statistics, and these other people are very well known seismologists. And they put together a list of data for the purpose of showing how repetitive earthquakes can be. And you probably can't read this very well, but the thing is that there are, about 30 different sequences in here. And I'll show you something in a little bit more readable form here. I took the top few sequences and the bottom few sequences. The top few sequences show magnitude 9.2 earthquakes, bigger than the one that occurred in Japan. These are from an area in Alaska. The last one was in 1964. Earthquake in Anchorage. There are 9 earthquakes in that sequence. Average time between them 682 years. The coefficient of variation is 0.23. What this group did was take these 30-some sequences and study the repetitive behavior of earthquakes. They were particularly interested in that alpha quantity over there, which they call the non-periodicity. So it's small, and the earthquakes are pretty periodic in this watch. Same deal as Garbled. These things were picked out of a sea of earthquakes because they appear periodic. And when you think about what's the selection group from which you could find these things, we had a time covering 6,000 years with earthquakes down to magnitude minus 0.7. So there would be billions of earthquakes if you count all the earthquakes of that size.
Can you say a little bit more precisely how alpha is defined, the non-periodicity factor?
It's a parameter fit to an inverse Gaussian probability density function. In this particular case, they tried with some other density functions. I'll show you in just a moment. We've got similar results. So it's a model-dependent parameter. But the point that they're trying to get here is that often these things are fairly small, kind of 3 or thereabouts, indicating quasi-periodic. And so good statisticians got carried away with this problem and fit these various probability density functions to those data. Did a perfectly fine job of doing that. But these are only on data that have been picked out of this sea of information. So all they're really doing is describing the examples they had. To try to say that this is a fundamental behavior of earthquakes, but it's really anything to do with earthquake forecasting and prediction, I think it is a gross mistake. And so a big part of my presentation here is to say when people who are mathematically sophisticated get together with people who are geophysically sophisticated, it's very easy to construct a problem that's fun to solve, but maybe have nothing to do with what we're trying to get to, which is to understand nature. And this group of people tried several different forms of probability density functions, the same ones that are in the table, and showed that as a probability distribution of time between earthquakes, they all look pretty much alike, except for this dashed line, which is a Poissonian function, and represents a Poissonian process. And they said, well, the data that we have are not fit at all by the Poissonian one, they're fit much better by these ones that are repeat, these quasi-periodic ones. And therefore, that's what's happening with earthquakes. And now these equations are actually used to make forecasts of earthquakes for insurance setting purposes and for essentially risk management. But what they didn't do is look at an unbiased sample. And my colleague Ron Kagan and I was also from UCLA, did a global study. We took all the earthquakes of magnitude 6 in the best catalog and looked at the times between them and the distances between them. Each one of these plots represents collections of pairs of earthquakes that are within a certain distance apart. And if you look at the fourth curve down there, those are earthquakes within about 100 kilometers. So earthquake happens, you look at it at 100 kilometers and see what's the rate, what the time index between earthquakes happen. And this is a logarithmic scale over here, and everything is normalized to some process. So what this is saying is that immediately after an earthquake, you get more earthquakes happening at a much higher rate than predicted by some process. And the closer you look, the more you see this excess earthquake rate. Just the opposite of what these other models are saying. Other models are saying that immediately after an earthquake, zero time down here, there's no chance of another earthquake happening. What's the difference? The difference is in how the data are selected. These guys looked through the entire catalog of earthquakes from planet Earth and found periodic sequences that
Dave, is there a minimum magnitude in this plot? Well, are you talking about
I have minimum magnitude of 6.
But for the previous one, they were not looking at average shocks, right?
So for these previous ones, these were just schematics of what the density functions look like. But for each one of the sequences, for each one of these sequences, these alpha parameters and so forth were fit using the magnitude, assuming that all the earthquakes in the sequence had the magnitude. One's at the top of the list, 9.2, one's at the bottom, tiny. So here's some questions that I would ask you to ask when you get involved with geophysicists, or when you're a mathematician, how will the data look? There's some say when an earthquake happens in the future, or when it can happen in the future, how do I say with it, well, what's the set for which the statistics are moving? What data were left out? What about all the 200 and some people who didn't get 7 points? This experiment repeatable. Is this something that has rules enough so that somebody else could look at the same set of data, the same universe of data, to get the same conclusions? And we're doing something just for fun, which is completely valid, and I don't mean to say you shouldn't take some data and fit an equation through it, but you should say right at the beginning, this is a mathematical exercise, and I'm doing it as an example of how the math works, rather than trying to draw statistical conclusions. And the question that's tough for me, what if answer defies your expectation? It's tough for me because I see so many examples of things where I think travesties were committed on otherwise good data or otherwise good math. And so I became so skeptical that I'm not sure that I'm open to an answer that may look simple or look classic, like very classic. And as you can see, I'm not doing a very good job. So let me talk about a way to get beyond that, a way to systematize the observations and the results of calculation in a way that we can make some conclusions of them that aren't dependent on these data sets. I'm going to give you a few definitions that I like to use, and I think pretty much let's go with some more I mean something purely probabilistic. A statement of the rate of earthquake occurrence per unit area, per unit magnitude interval, per unit time. And the fact that that might be low is also information. So that's probably an earthquake prediction is a special case. A special case where the probability is so high that you ought to do something different from what you normally do. So from a forecast, you decide if you get insurance or not, decide where you're going to live, and from a prediction, you decide whether you're going to set out a particular experiment and you're going to get your equipment to take it to place, or you're going to run away. This experiment called Realm was done again in Southern California and then expanded to all of California. The idea was basically to produce some source models for use in hazard calculations and to test some assumptions that are commonly made about earthquake. And here's some parameters: magnitude 5 and above, 5-year test period. This is latitude, longitude blocks. We had a grid, specific grid to define pixels as essentially the value of probabilities, and had a magnitude range. And so the assumptions that we wanted to test in this process was that the magnitude of earthquakes is limited by the length of the fault, that the slope of that Victor curve varies from place to place, that probability increases with time since the last earthquake is proposed by this sort of standard model, and whether we can express calculations that actually tell us something about earthquake. And back in I guess about 2002, we collected models of earthquake probability. There were actually 17 of them, but 16 were shown here. And it was a huge revelation just to see how different they are. They're all plotted for the first time in increased color scale in the same areas. Just some dark areas where the models have been plotted. But you can see some of them have very high resolution, special resolution, some don't. And some are very speckled, and some have earthquakes occurring on faults. And we made a kind of a mistake when we set up this experiment. We basically took cells, geographic cells, and magnitude cells, said, okay, there's a certain probability of earthquake occurring in a 5-year time period. And that's random in this situation. Omega is the number of earthquakes that occurred in that cell. We use the Poisson probability to characterize that. There are a couple of problems with it. First of all, the earthquakes are not independent. You get one, you're going to get one. That was shown by this Poisson. And the Poisson model assumes that they're going to be independent. So that's wrong. Another more subtle thing we didn't fully recognize at the beginning was that, let's say you simulate earthquakes by this process. You won't always get the same number of earthquakes. And when you're evaluating what actually happened, then what score you get, the negative score you get by taking the log of this and adding it up itself, depends a lot on the number of earthquakes that actually occurred. So some models that just by luck happen to score well on the right number of earthquakes also scored well on this one. So what we decided to do in retrospect was to normalize the probabilities. So take the whole map and the whole magnitude range, add up all the lambdas, and then divide by the total, so that the lambdas are now proportional to the area that we do the relative probability. And we also invented a scheme that I'd love to have some feedback on, because I hadn't seen it in the literature. And I asked some of my more statistically friends that was it's basically a double difference likelihood test. And the way it works is that we have two different models of earthquake behavior, like the one shown in the 16 picture. We simulate earthquakes according to each one of those models, and then we score their likelihood according to their own likelihood and according to the other models' likelihood. So here the green dots were all calculated for simple Watsonian null hypothesis 1. And the red dots were all done on a model that basically has quasi-periodic behavior built into it. Then the red dots we scored the log likelihood, assuming a quasi-periodic model. That's a standard likelihood test. But we also on the vertical axis scored those according to the other one, the assuming null. So each of the models generates some synthetic earthquakes, and those are tested against both hypotheses. And then we measure essentially the fraction of those simulated earthquakes that fall above or below this blue line, which has a constant double difference in one likelihood. And we get curves that look like this, and again, the green one is the null hypothesis, and the red one is the and you can reject it if they fall into the yellow area. In this case, you can't in one of those models, even though they're pretty different. So, I don't have a name for this, and if somebody's seen this, please tell me so that I can refer to it. Anyway, this realm procedure has completed and finished the 5-year test, and the model that scored best was one that had very high resolution, and which presumed that magnitude 5 and above earthquakes would occur more or less in the places outlined by magnitude 2. Bit of a surprise. Anyway, this idea has been extended now to a number of different areas, including the whole Earth. And we introduced more testing results, modified the test, trying to test not just the locations of the epicenters of the earthquakes, but also the endpoints of all pressure. And we had variable time windows from 1 hour to emergency purposes and 5 years of and it does more models with larger magnitude thresholds, because most people would say, yeah, magnitude 5 is huge. Let's talk about it. And here is a map showing where earthquakes occur, and for those who study plate tectonics, you will recognize that the earthquakes are occurring along the...
Can you just remind us what the two catalogs are that you're using, CMT and
Oh, yeah. CMT is the best catalog in the world because it uses many hundreds of stations and uses the whole seismogram to get what's called the moment, which is related to the magnitudes of an exponential function. The best measure of this size. The PET catalog, which is represented here, is preliminary determination of epicenters. This is a quick and dirty catalog, but actually it's revised within a month. And it's no longer preliminary because it's, in some ways, the most stable catalog because after this month it isn't revised again. And the point here is there are a lot of earthquakes, so if you're going to do a statistical test, you like and what we've done is taken a very, very simple model in which we use a smoothing function on each earthquake. And it's very much like maybe a smoothing function that we show in the tutorial session. And we just overlay these to get kind of an average estimate of the earthquake probability if you on that. And what you see here is that the red zones follow the plate patterns. That's where most of the earthquakes occur. But the probability is considerable for some fairly wide region around those plate patterns. And this is kind of an invitation to the black swans. Basically a geographical representation of a head-to-tail distribution. So you're going to have places that haven't had earthquakes in the past, but if they're within a few hundred kilometers of places that have had earthquakes, you need to consider that earthquakes bigger than 5 and black extension of the other bigger than 7 or 8 are also considered. We do the same thing on a short-term basis, the daily forecast based on what's happened in the last couple of weeks. And one of the things we're now building into this model is the fact that there are different tectonic regimes. This model shows those tectonic regimes on the map. The ones that are most interesting are the red zones here, which are primarily subduction zones. So one plate is being pushed down beneath the other. Contact area is fairly great. Stresses build up over the grace. That's where the biggest earthquakes occur. And our model says that any one of these red zones here can have a magnitude 9 earthquake with reasonable probability. The other colors also have not quite magnitude limits, but characteristic magnitude, corner magnitude, which earthquakes become much less likely. But the point is here that now we have a fairly detailed model that has built into it some physics, a lot of experience. And these things are quantifiably testable and can be put on the one conclusions are selected data bad, avoid that problem at all costs. It's difficult because we know most of the history of earthquakes. We have to use that history, but we can't rely on it. We're making prospective tests, which I think are much more reliable. And seismologists need a lot of mathematical and statistical help in all of these problems. Thanks very much.
I have a question. There's a fairly well-known model for the clustering that you mentioned over time by Hawks in the 1970s, which you know, I presume.
Yes.
That model is the one that says that the Poisson density evolves in time, and it increases or decreases according to the number of earthquakes that have occurred.
Right.
And it's been a very successful model in many other fields, for example, in modeling defaults in financial markets, and in modeling crime in Los Angeles. There's a professor at UCLA who did the work.
Yes.
And how come you didn't mention it?
There's a lot I didn't mention.
No, but this particular one, because that's a rather very successful model, I thought.
It hasn't been developed to the extent that some versions of it have been developed by other people. I mentioned Yoshio Ogata from Japan, who's developed a method which adapts many of the same ideas from the concept model, specifically to earthquakes. And my colleague Kagan at UCLA, same can't say anything about crime and stock markets and so on. But anyway, these models are essentially concept models that have been optimized.
Cox or Hawks?
Hawks.
Hawks.
I'm Dorian Abbott in Chicago. But you showed at one of your last slides that areas near major earthquake areas have some probability of earthquakes happening. But I was wondering, if I understood properly, there was some sort of geographical smoothing of the actual data. And so I was wondering how much that smoothing they use would influence such a conclusion.
Good question. It influences a lot. And the smoothing isn't completely arbitrary. You optimize the smoothing distance by taking learning set and the test set and found that the smoothing distance that best fits earthquake occurrence going from past to future. And so what I showed was using all the data we have now and ready to test against earthquakes that haven't yet happened. The point of it is that when you get earthquakes like those in Haiti and other places that are very tragic, and it's easy to say, nobody predicted that. Why didn't we know? Well, I think in the case of Haiti, we should have known, and these kind of models actually show reasonable probability there. But there are a lot of places that have low probability by themselves. Single out, they look low. Add them all up, and some earthquakes are going to happen in those zones that we found. very good job of predicting future events. But not perfect, and you definitely have to allow for this.
Yuri Bielka, UC San Diego. I'm not sure I want to put on the hat of a defender of particle prediction experiment, but to be completely fair, when the prediction was made, you mentioned the 95% confidence limits, but the other part of the prediction was that within 30 years there's going to be 100% likelihood of an event happening in this particular place, and in that respect, with that matrix, this prediction was successful.
Okay, that's a pretty weak form of prediction, but it's true enough. Yeah. I think those.
And the second part of the question is, how many of particle-like events would you need to be convinced that quasi-periodic model roughly works?
There's your question. That gets to my as a skeptic. I'd say about 4 or 5 more. I mean, already the timing is well up. The reason I need 4 or 5 more is that those first 3 earthquakes are kind of unknowns in the system. The magnitudes are not unknown, even the locations are not. So I want to see some earthquakes that actually are going to occur on the center of partly, and I want to see a definition of what those earthquakes are going to be, and then 3 or 4 more earthquakes like that.
So 7-point flips is a magic number.
I don't know if there's a magic number. It depends on how precise the forecast is.
Maybe we have to go to the next topic. There'll be a lot of comments in the discussion.
So, Michael at UCLA, I mean, is there any sort of model or physical model of earthquakes that has dependence in both space and time? In other words, what I'm aiming at, if you had such a model, and for certain parameter values it would predict nearly periodic behavior, would that strengthen your belief?
There are models, and I think the ones that come closest to what you described are cool stress models, in which you take all the earthquakes you know about, the faults that you know are moving below the surface, you add up the stress accumulation for those, and then identify some sort of rupture criteria from those earthquakes that occur. Lots happens. You have physical lasting motion, lower cross, and it's a pretty hard job. Like the coin toss and the particle earthquake, there are some very similar sequences of earthquakes, just like this cool stress model.
So these actually produce simulated catalogs?
Yes. They do.
Including location?
Right. But they're good on selected examples and not good on open-ended